Here's a question that trips up a lot of people, including some who are pretty good at maths. Is 0.9 repeating actually equal to 1? Not close to 1, not basically 1, I mean equal to 1. Most people's guts say no, and today we're going to find out why that gut is actually wrong. This isn't a trick, there's no sleight of hand here. This is a genuine probable mathematical fact, and by the end of this video, you won't just believe it, you will see why it can't be any other way. Okay, now this is the most common reaction, and it goes something like this. Sure, it never gets there. It may get closer and closer to 1, but it never surely gets there. There's always a tiny gap, an infinitely small gap, but it's a gap nonetheless. Let's start with the simplest proof. One that needs no calculus and no algebra, just fractions. You already accept that 1/3 equals 0.3 repeating. That's just long division. Try it yourself. Now multiply both sides by 3. On the left, one side times 3 is 1. On the right, 0.3 repeating times 3 is 0.9 repeating. So 1 equals 0.9 repeating, and that's it. If you trust your fractions, you have to trust this. And here's a second way to see it. And this one feels almost like a magic trick. Let's call 0.9 repeating x. Now multiply both sides by 10, you get 10x equals 9.9 repeating. Here's the clever bit. Subtract the first equation from the second. 10x minus x is 9x. 9.9 repeating minus 0.9 repeating. All those 9s after the decimal cancel out perfectly, which leaves exactly 9. So this means that 9x equals 9, which means x equals 1. But x was 0.9 repeating, so 0.9 repeating equals 1. The decimals didn't round, they cancelled out perfectly. That's not a coincidence, that's what infinite decimals do. Now I can already hear the objection. But it never reaches 1, each step gets closer but you never actually arrive. And you're right, that the sequence never stops. But here's the thing, 0.9 repeating isn't the sequence, it's not the journey, it is the destination. When we write 0.9 repeating, we're not describing a process that's still going. We're naming the number that the sequence converges to, the limit, the endpoint. And that limit is exactly 1. This brings us to something deeper. What actually is a real number? It's not a string of digits. Digits are just names we give to numbers, like how London and the capital of England are two different names for the same thing. 0.9 repeating and 1.000 repeating are two different names for the same point on the number line. Real numbers are locations, and this particular location has 2 decimal names. That's allowed. In fact, every integer does. 1 is also 0.999 repeating. 2 is also 1.999 repeating, and so on. If you want the most rigorous version, the one that mathematicians are most happy with, it comes from the geometric series. 0.9 repeating is the same as 9/10, plus 9/100, plus 9/1000, going on forever. Factor out the 9, and you've got 9 times the sum of 1/10 to the power of n, from 1 to infinity. Now there's a formula for this. When the ratio between terms is less than 1, which it is here, it's 1/10. The infinite sum converges to r over 1 minus r. Plug in 1/10, simplify, and you land exactly on 1. No approximation, no rounding, exactly 1. What happens when we add up the terms one at a time? The first partial sum is 0.9. The second is 0.99, then 0.999. Each step we get closer. The gap between our sum and 1 gets 10 times smaller every time. After infinitely many steps, the gap is 0. The dot lands exactly on 1. Here's the cleanest way to think about it. If 2 numbers are different, you can always find the number between them. Always. And that's a fundamental property of real numbers. So ask yourself, what number sits between 0.9 repeating and 1? Take your time. There isn't one. There's no room for anything between them, and if there's nothing between two numbers, they're not two numbers. They have to be one. So what's the real takeaway? Every real number that ends in all nines has a twin, a cleaner way of writing the same value. This isn't a flaw in our number system, it's actually a sign that it's working correctly, that the real numbers are complete with no gaps. And the deeper idea here, that infinity isn't a process, it's a completed thing, that idea shows up everywhere in mathematics, in calculus, in limits, in the very foundation of how we define numbers, which, as it happens, is exactly what we're looking at next time.